In this video, we are going to solve two examples on the topic of mathematical induction. In the first exercise, we are given cosine of x as a y function. Then we are asked to prove that nth derivative of y is equal to the cosine of x plus n pi over 2. Again, you can see the description of the problem. Typically, we have 3 steps in using induction rules. At step 0, we state the proposition. In the next step, we prove that the relation is true for n equal 1. So we know the first derivative of cosine x is minus sine of x. How to convert sine to cosine? From trigonometry rules, we can calculate the cosine of a plus b in argument as a function of cosine and sine of a and b. Now we can relate the sine of x to the cosine of x plus pi over 2. So we can see that this relation is true for n equal to 1. Now, in the next step, we assume that the relation is working for n equal to k. So kth derivative of cosine x is the cosine of x plus kp over 2. In the last step, we try to prove for n equal to k plus 1. So we need to calculate the kth derivative of cosine x. It is actually the derivative of kth derivative of cosine x, which we obtain in the step 2.1. Derivative of cosine x plus k pi over 2 is the minus sign of the same argument multiplied by 1, which is the derivative of argument. Now we need to use some trigonometry rules. First, we use the sine rule for sine of x, which is minus sine of x is equal to the sine of minus x. Second is the sine of argument is equal to the cosine of pi over 2 minus that argument. By using these two relations, we can prove that the equation is true for n equal to k plus 1. So we can conclude that the result is true for n equal to 1, and if it's true for n equal to k, it is also true for n equal k plus 1. Therefore, the result is true for all integer positive n by the principle of mathematical induction. The next exercise is application of induction rule in the sequences. In exercise 2, we are given a recurrence formula with u0 and u1. Then we are asked to show that un as a general rule is equal to the 3 to the power of n minus 2 to the power of n plus 1. So no matter the problem, the steps in using induction are the same. Again, we state the proposition as you can see in the first step. Now, because the general recurrence equation is dependent on the two previous terms in the sequence, we need to prove that the general formula is working for the first two terms, which are n equal to 0 and n equal to 1. So substitute 0 and 1 in the general formula, and we see this worked for both. Then in the next step, we assume that the general formula is working for n equal to k and n equal to k plus 1, last two consecutive terms. In the last step, we try to prove it for n equal to k plus 2. To do so, we write the recurrence equation for uk plus 2 and use the result of step 2.1, substitute the values for the uk plus 1 and uk, and you can see the red expressions are substituted values from 2.1 step. We rearrange the result and merge the terms with the same bases of 2 and 3. Now we factor out 3 to the power of k plus 1 and 2 to the power of k plus 2. Again, make the equation more concise by merging terms having same bases. Now we can see that the final result is true for n equal to k plus 2. So we can conclude that this is true for any positive integer. The formula works for n equal to 0 and n equal to 1. And if it works for n equal to k and n equal k plus 1, then it also works for n equal k plus 2. Therefore, the formula works for all positive integer by principle of mathematical induction. Thank you for watching this video.